This topic is heating effect of current. So if we assume that we have a resistor, a pure resistor with one source EMF. So if we consider a purely resistive circuit, that a circuit only consists of only some resistor and a source EMF, that then the energy of the source get dissipated entirely in the form of heat produced in the resistor. That means if you have a circuit like this and there is a resistor and there's a source EMF, then the energy this EMF is going to give to the circuit is going to dissipate at the resistor. All the energy will be dissipating at the resistor in the form of heat, okay, in the form of heat. And this phenomenon of production of heat in the resistor by the flow of electric current is the heating effect of current, or Joule's heating. Very simple. This you have done before in your junior classes as well. Now, why does this happen? Like, why does this heating will happen? Because when the electrons are flowing, okay, because of the electric field, then the electrons are flowing. Those electrons are going to collide with the other electrons and the metal ions also. So read this whole thing carefully. So when the potential difference is applied across the end of the conductor, then you know that potential difference applied will establish an electric field and its electron will get accelerated in the opposite direction to the applied field. The speed of the electron does not increase beyond a certain constant drift speed. That also we have discussed, that drift speed, drift velocity remains constant. And this is because of during the course of the motion, the electron collide frequently with the positive metal ion. Now, these electrons will have some kinetic energy which they have gained by the electron during the interval of free acceleration between the collision. So electrons will gain some kinetic energy between two collisions that we have done before, and the metal ion begins to vibrate because this kinetic energy is transferred to the metal ion. When the electron collide with the metal ion, then they transfer this kinetic energy to the metal ion, and the metal ion will begin to vibrate. They will begin to vibrate about their mean position more and more violently. So the average kinetic energy of the ion will increase because they are vibrating more and more violently, because they have got the kinetic energy from the flowing electron. This increase in the temperature of the conductor. Thus, the conductor gets heated due to the flow of current. Okay. Now, obviously, the electrical energy supplied by the source of EMF is converted into heat. Very simple. Now, what will be the what will the expression of this heat? We are going to derive the expression. How much heat will be produced by this current, and that's called the Joule's law. So, how to calculate that? Now, think about a very simple circuit with a EMF source and a resistor. Now think about the EMF source. Think about this source. So you have a resistor here and the source EMF here. Now we know that work done by this EMF source is equal to the charge which has to be taken around the circuit across the potential difference. That you have done in your potential chapter also, that is work done is equal to charge times the potential difference. Very simple. Now the work that this cell is going to do, is going to be lost as heat at the resistor. Okay, at the resistor. So this EMF is doing the work and this EMF is losing energy. You already know this. If work is done, then energy is lost. And this energy is lost in the form of heat at this resistor. Okay. Now what is this heat loss? So heat loss will be simply the work done work done by the EMF. So how much is the work done? Q times V, and we can then say that as the charges as the charges move through the conductor without suffering collision, their kinetic energy would change, so the total energy is unchanged. So don't need to get confused about this. Simply remember that the kinetic energy gained by these electrons will be is equal to the Q times V, and Q you can write it as I into T times V. So that is what the heat that is gained by the resistor, heat dissipated at the resistor becomes VIT. Very simple. Now you know that according to the Ohm's law, V is equal to IR, and as V is equal to IR, this very expression you can write it as these two form also. So heat will be is equal to VIT in joules, or I square RT, because V is equal to IR. So you can convert that I square RT and V square by R into T. Now, because these are all in the unit of work, because you have converted this from the kinetic energy work done expression. So this will have the unit of work. And if you convert that into unit of heat, then you have to convert into calorie by dividing 4.18. Next topic is electric power. So electric power is also simple. You already know power is equal to work done over time. Okay, power is equal to work done over time. Read this definition, basic definition: the rate at which the work is done, by the source of EMF in maintaining the electric current through a circuit is called electric power of the circuit. Simple. Or the rate at which the appliance convert electric energy into other form of energy is called electric power. For example, if you have a 100-watt bulb in your house, it means it is converting 100 joules of electrical energy. It is converting electrical joule of electrical energy into light energy every second. Okay, every second, because 1 watt is equal to work done over time. So work done means joules over second. Now, obviously, the bulb is not 100% efficient, so some amount of power will be lost. We'll be doing it then. Then power will have these formula as well. P is equal to V into I square R, and V square over R. Very, very simple. All these topics you have done in your class 10. Class 10, you have done all these topics. So this is just a simple revision. Now, what will be the unit of electrical power? Again, power will be work done by time, joules by second. That will be watt. Okay, so SI unit of electrical power is watt. The power of the appliance is 1 watt if it consumes the energy at the rate of 1 joule per second. Okay, 1 joule per second. So what will become 1 joule per second? You can convert it. It will become 1 watt is equal to 1 volt per ampere also. How? 1 joule per second. So you can just multiply and divide this expression by 1 coulomb. Multiply and divide by 1 coulomb. So joules per coulomb will become volt. Okay, that is work done by charge, and coulombs per second will become current, that is unit of ampere. So it will become 1 watt is equal to 1 volt per 1 volt times 1 ampere. Again, bigger unit of watt will be kilowatt and megawatt. Commercial unit of power is also considered as a horsepower. So if you go to the market to buy some heavy electrical equipment, then you will have to state in the terms of HP, horsepower. So 1 horsepower is 746 watt. But do remember, horsepower or 746 watt, this quantity is not a SI unit. This is not an SI unit, and this you cannot multiply this value and get this value here. Okay, this is just a commercial used power unit, and this does not have any SI system validation. Then next is electrical energy. So electrical energy, just hold on. So what is electrical energy? This is also simple. The total work done or the energy supplied by the source EMF in maintaining an electrical current in the circuit for a given time is called electrical energy consumed in the circuit. Very simple. It depends upon the power of the appliance and the time for which this power is being maintained. For example, if you are using a 100-watt bulb, if you are using a 100-watt bulb for 10 minutes, for how much? 10 minutes. So time is equal to 10 minutes. So the total electrical energy will become 100-watt power into the time. Time is 10 minutes, but minutes is not an SI unit. So you have to convert this into second, and that will become 100 times 600. And that will be 60000 joules. So this is the total amount of energy which is consumed by this 100-watt bulb in 10 minutes. Very simple. So 1 joule again watt per second, and that's what your LSI unit of electrical energy is, also joules. Then commercial unit of electric power. Commercial unit means the unit that is being charged by you by the power company. Okay, your power company is supplying some electrical supply that you give the electrical bill to every month. So that how is that electrical bill is calculated? So that 1 unit, what generally understood term of 1 unit is 1 kilowatt hour. Okay, and that is how it is calculated. So 1 unit. Okay, 1 unit of electrical unit, 1 kilowatt hour is defined as the electrical energy consumed by the appliance of 1 kilowatt in 1 hour. Okay, and that is your commercial unit of electrical energy. 1 kilowatt hour would means using a device which is 1000 watt for 1 hour. Now 1 hour again is not an SI unit, so 1 hour would become 3600 seconds, and that would amount to this many joules of energy. So 1 kilowatt hour would become 3.6 into 10 raised to 6 joules of energy. Then the next topic is power rating. Now, power rating is a very important as well a bit confusing topic. Now, what is a power rating? You see, any electrical equipment or electrical appliance which is being sold to you, let's say you go to the market to buy a fan and a light bulb. So this fan and light bulb will be specified. There will be some place on the fan and the light bulb, there will be written about the power rating. Power rating has to be specified. Now, what is power rating? Power rating is these two value. It will be specified like this, let's say 220 watt, and the power is 220 volt, and the power is 80 watt. This piece of information is called power rating. Now, what does it mean? It means that if you use this fan under the potential difference of 220 volt, then this fan is going to consume 80 watts of power every second, 80 joules of energy, 80 joules of energy every second. But only if it is given this volt, this potential difference. If you give a potential difference other than this, if you don't give 220 volt, if you give 330 volt, 110 volt, anything else, then it may not consume 80 watt. It may consume more or less depending upon what you have given. But this is called, this piece of information is called the power rating. Now, power rating of an electrical appliance. Power rating of an electrical appliance is the electrical energy consumed per second by the appliance when connected across the marked voltage of the main. Marked voltage. So this is our marked voltage. You know that we all get 220 volt. So that is our marked voltage. Okay. Now from this piece of information, what you can calculate, because you know power is equal to V square by R. So you can always calculate the resistance with this particular formula. You can calculate the resistance from this information. If a voltage and power for any appliance is given, then you can calculate the resistance of the appliance. Okay, you can calculate the resistance of the appliance. Now, you have already done in your junior classes as well that electrical appliances or power connection in the home, household circuit connection is done in parallel. You have done this pretty well in your class 10 syllabus, that home electrical circuits are connected in parallel. So we are now going to understand what will happen if they are connected in series, not in parallel. Okay, which actually doesn't happen. I mean, we don't connect these appliances in series, but what will happen if we do connect them in series? Okay, if we do connect them in series. Now, when you put multiple bulbs or any appliance in series, circuit will look something like this. Okay, this is your circuit, this is your external potential source, and these are your three devices. All three devices have different power, P1, P2 and P3, and all three devices have a rated voltage of V. Now do not get confused with this V. This V is the rated voltage. This is rated voltage. This is not the actual potential drop across each. The actual potential drop across these might be V1, V2, V3. Okay, the actual potential drop might be V1, V2, V3, but this V which is given here is the rated voltage. Okay, the voltage rated for the appliance given by the manufacturer. Now, when you place such device in series, so if you place them in series, then we know that their resistances, the equivalent resistance will add them up. So first we need to find the resistance for individual. So R1 will become what? V square by P1. R2 will become V square by P2. And R3 will become V square by P3. Because we already have this formula, P is equal to V square by R. So we are simply using this formula to find the individual resistances of these device. Okay, now we know the resistance, individual resistances of this device, and because these devices are connected in series, then their resistance will be, equivalent resistance will be how much? It will be R equivalent is equal to R1 plus R2 plus R3. So their equivalent resistance of the whole combination will become what? R1 plus R2 plus R3. Okay. So if P is the effective power of the combination, then it will become how much? V square by P, which is the effective power of the combination, V square by P1, that is R1, V square by P2, V square by P3, and you can take this V out, and this is what you're going to get as the effective power of this combination. Now, effective power of the combination, as you can see, is less than the individual required power. This is one of the reasons that we don't use this in series. Because if we connect them in series, you see what the effective power is simply the reciprocal of the sum of the reciprocal of the individual powers. That means individual device, each device is not going to get the power which is required. So that is the reason why we do not connect them in series, because none of the device is going to get the required power to work effectively. So for a series combination of the appliance, the reciprocal of the effective power is equal to the sum of the reciprocal of the individual power of the appliance, and effective power will become P by N. By this way, we can actually calculate the current in the circuit. Very simple. Current will be the applied voltage divided by the total resistance. The bulbs are connected in series, the current I through each bulb. Because they are connected in series, that means the current which is flowing in each bulb will be same. The same current is going to flow. Okay, in all these appliances, same current is going to flow, and that is the reason why V by the total current of the circuit will be V over R1 plus R2 plus R3. This value here, very simple. Now we need to calculate what is the actual power. Now previously P1, P2, P3 we have used P1, P2, P3, these values. These were the power which was rated, the rated power. Rated power means that the power which was rated by the manufacturer, that this device is going to consume when it is applied with this specified voltage. This is the rated power. But that does not mean that the device is going to consume the rated power only. The device may not consume the rated power because each device is not getting the same potential drop. So what would be the actual power consumed by the individual device? Now you already know the current, you have just calculated the current here in the circuit. So according to this current value, we can calculate the actual power consumed, that will become P1 dash. So P1 dash will become I R1, P2 dash will become I R2 and P3 dash is equal to I R3. So this will be the actual power consumed by individual appliances. Now, as you can see that R is inversely proportional to P. Okay, so the device which has the lowest power will have the highest resistance. Okay, the bulb of the lowest wattage or power will have the maximum resistance. Okay, and the one which has the maximum resistance, potential drop across it will also be maximum, because we know V is also proportional to resistance. That means the device which has the lowest power will have a higher resistance, and being a higher resistance, potential drop across that device will also be very high, and that is why that device will glow with the maximum brightness. That device is going to glow with the maximum brightness. Now do remember that P is equal to VI, because in this circuit the current is same for all the resistors, so the power would depend upon the potential drop, and the potential drop will be maximum, so it will glow with the maximum brightness. And when the current in the circuit exceeds the safety limit, the bulb with the lowest wattage, this bulb which was glowing with the maximum brightness, this bulb is going to fuse first. It is going to fuse first. Why? Because it is glowing maximum brightness, higher the current, more power will be dissipated, more heat will be generated at the resistance, and the resistance wire will burn off. It will get fused first. Fusing means basically that the resistor wire has heated up more than its melting point, and it will then break off the circuit. It will get fused. Now the next is, if we place this in the parallel combination, power consumed by parallel combination. So in the parallel combination, you place these three devices in parallel, and when you place them in parallel, then you already know that the potential of the applied potential will be is equal to the potential in each device. Okay, applied potential will be is equal to the potential of the each device. Now again, individual resistance value you can very well calculate by using the power rated power. You see, this is the rated values. These are the rated values, as you can see, v square by p1, v square by p2, v square by p3, and according to these three you can calculate the r1, r2, r3. Because these resistances are in parallel, so the effective resistance will become 1 by r1 plus 1 by r2 plus 1 by r3. That will be your effective resistance in the circuit. Now effective resistance in the circuit, then we can also find the we can also find the total power, effective power in the circuit. How can we find? Just multiply the whole expression, multiply this whole expression by v square. So v square, v square, v square, v square, and then it will become what? The effective power is equal to p1 plus p2 plus p3. That means for a parallel combination, the effective power is equal to the sum of the powers. Okay, and that is why effective power being the sum of the power, that is why we use a parallel combination, because as the effective power is the sum of the power, that means every device is going to get the power which they require. Okay, every device get the power which they require to work effectively, and that is why it is connected in parallel. Now again, we know that this value R is proportional, inversely proportional to R is inversely proportional to P. We know this. So the resistance of the highest wattage, because R is inversely proportional to P. So if the wattage, that power is very high, then the resistance will be very low. So resistance of the highest wattage, will be minimum. Okay, that resistance will be minimum. And then because that resistance is minimum, that means, let's say this resistance R1, this is minimum. So maximum current is going to flow through this one. We know in the parallel circuit that the potential drop V is same for all the line. So the current is going to flow, maximum current is going to flow through the circuit which has the minimum resistance. Maximum current is going to flow through the circuit which has the minimum resistance. And that is why here the resistance which will be minimum, and which resistance will be minimum? The one which has the highest wattage. Okay, it is going to blow with the maximum brightness. And if the current in the circuit exceeds the safety limit, the bulb with the maximum wattage, that is the bulb with the minimum resistance, the bulb in which the maximum current is flowing, will be fused first. Okay, and for this reason the appliances in the house are connected in parallel. Now the next topic is efficiency of the source EMF. Now we already know that there is an internal resistance to the cell. We already know that there is an internal resistance to the cell, and there will be a potential drop within the cell itself. Okay, we already know that. That means the maximum work, the maximum work this cell is going to do is the work that is done in the external and the internal. But you as a user is not going to benefit anything about this internal potential drop of the cell. This is of no use to you. So only this work done, or this power dissipated at the external resistance is good for you. This is not for you. This is of no use to you. So what we see, this we consider as the output power. Output power. Okay, this is considered as an output power, and the whole thing, the both combined, this and this combined, will be the input power. Okay, this will be input power. So input power is the total work done over time by the cell. Input power is a total work done over time by the cell, or the total power a cell can deliver in the whole of the circuit. And output power is only the power which is dissipated at the external resistance. Now output power will be is equal to V into I. Why V into I? Because we know that the potential drop in the external resistance is V, and input power would become E into I. E is the EMF. EMF is the total work done by the cell. Okay, total work done by the cell, and that is why we take it as E into I. So I will cancel, and it will become V by E, or simply you can write it as IR by I plus R, and you will get this value as your efficiency. This is your efficiency. So this becomes our efficiency. Output power by input power, that is R over R plus small r, that is internal resistance. Now next is maximum power theorem. Now maximum power theorem states that the output power of the source of the EMF is maximum when the external resistance of the circuit is equal to the internal resistance of the source. Now why is that so? So let us understand. Let's do the derivation. Very simple derivation. Now consider that you have this circuit. Okay, you have this circuit, and in this circuit again you have an external resistance, and there's a potential drop across the external resistance. Okay, and then you have an internal resistance of the EMF. Now, and there's a current which is flowing in the circuit. So the EMF E, internal resistance R, external resistance of the device capital R, and the current would become the total EMF by total resistance E divided by R plus R. If you consider power in this case, so P is equal to I square R, you know that, and I can be written as E by R plus R whole square times this. So you will get this expression. You'll get this expression. Now this is the power. That means if power has to be maximum, if this value has to be maximum, then this value, the one in the denominator, has to be minimum. Okay, this has to be minimum. And if this has to be minimum, then you can convert this expression r plus r whole square, a plus b whole square is equal to a minus b whole square plus 4ab. You know this formula, so it will become r minus r whole square plus 4r into r. This value cannot be zero because capital and the small are real numbers, so this cannot be zero. And this value can be zero. This value can be zero, but when it will be zero, it will be zero when small r and capital R are both same. So if this is the condition, then this whole value becomes zero. And if this value becomes zero, that means this expression will have a minimum. That means this denominator will have a minimum value then. Okay, this denominator have a minimum value and the power will be maximum. So the maximum power in this case will be when r and r are both same. And if they are both same, then your total power in the circuit will become this value here. The maximum power output of the source is this value. So because r and capital and small r has both become same, so this will become your this value. This is the maximum power output of the source EMF. Now what would happen if you short a battery? Shorting a battery means that if you have a battery with some internal resistance and you do not give any external resistance, no external resistance, this means shorting a battery. Okay, you have shorted the battery. So shorted the battery means no external resistance, and no external resistance means R is equal to 0. If R is equal to 0, then your same expression will simply become E square over R. That will be your current because capital R is 0, and this will be the power dissipated inside the battery. Power dissipated inside the battery, and a power output will become 0. So maximum efficiency of the source EMF. Now we just now understood that the source EMF, the maximum output power will be when capital R, small r is both same, internal, external resistance both same. So, and we have already calculated the efficiency. So this is our efficiency. We have just calculated this efficiency here, R divided by R plus R. And the maximum power delivered to the maximum output power is equal to, is when these two values are same. So your maximum efficiency will become 50%. So the efficiency of the source EMF is just 50% when it is delivering maximum power.